Okay, so we're going to wrap up chapter 10. Here's a quick review about induction. To prove a statement Sn is true for all natural numbers n, a common technique is to use induction. So the technique works like this. You prove that the first statement is true. You assume the statement is true for some natural number k, so Sk is true, and prove, using this assumption, this inductive hypothesis, prove that Sk plus 1 is true. Combining these two steps, you can therefore conclude by induction that all the statements Sn are true. Okay? So we investigated this problem of the Tower of Hanoi. You have, so it's a puzzle consisting of a board with 3 dowels and a collection of n disks of n different sizes. The disks have holes drilled through the center so they can fit on the dowels on the board. Initially, all the disks are on the first dowel and are arranged in size order from the largest on the bottom to the smallest on top. The object is to move all the disks to another dowel in as few moves as possible. Each move consists of taking the top disk off of one of the stacks and placing it on another stack, with the added condition that you may not place a larger disk atop a smaller one. And then this figure on the handout shows you how to solve the Tower of Hanoi in 3 moves when n equals 2. Okay, so what you investigated with this problem, you came up with this chart that for up to 7 rings, we listed the minimum number of moves to solve the Tower of Hanoi game, and this pattern emerged. Right? It looked like these are numbers were one less than a power of 2, and so that actually is the theorem we're going to prove, that the Tower of Hanoi game can be solved in 2 to the n minus 1 moves. And we're going, so n is a natural number of rings is a natural number. So this is a statement for all n, for all natural numbers n, the Tower of Hanoi games with n rings can be solved in this many moves. So this sets up for a proof by induction. Okay. So the theorem proved. So the proof goes, the Tower of Hanoi game can be solved with n disks can be solved in 2 to the n minus 1 moves. So I'm just going to kind of abbreviate here. So n disks can be moved in 2 to the n minus 1 moves. Proof. Okay, so we will use induction. Basis step. We need to prove that this statement is true when n is 1. Well, is it obvious that one disk can be moved to another peg in 1 move, right? So one disk can be moved to another peg in 1 move. That's outside of the formula. 1 equals 2 to the 1 minus 1. 2 minus 1 is 1. Okay? So it's true. So the basis step is proved. So let's talk about the inductive step. Now suppose we're going to assume that this game can be solved with n disks can be solved, our k disks can be solved in 2 to the k minus 1 moves. Okay? So now assume k disks can be moved to another peg in 2 to the k minus 1 move. So what do we need to show? So keep in mind what we need to show for this inductive step. We need to show that for k plus 1 disks, we can move it in. It's going to be 2 to the k plus 1 minus 1 moves. And we're only going to use this assumption right here, this inductive hypothesis. Okay. So, how do we go about proving such a thing? You see how this is different from a lot of the proofs we've done. There's no real definitions to unravel, no sets, notation. We're just talking about like physical objects. I mean, something. It's kind of a different kind of a statement. So, what do we think?
So that 2 to the k minus 1 minus 1 can be done.
Going backwards? What we're saying? So we're showing we need to assume we have k plus 1 disks. Okay. So now start with k plus 1 disks. I need to show that I can move these to another peg and 2 to the power k plus 1 minus 1 moves. Think about your experiences. How did you find these solutions? Did you notice anything, any kind of patterns? Like the physical process of actually moving these stacks. Did you notice that before you could move the very bottom peg, bottom ring, you had to restack all the rings on top of it onto another peg? Because you had to have a free space to move that biggest ring. The biggest ring could only move to an open space. So if you want to move the last biggest ring over, you first have to take the stack on top of it and move it all over onto another peg. You should know how many moves it takes to move the rings on top over to another peg, because you just did that problem. Yeah. So think about this. If we have k plus 1 disks, the biggest one, you leave that alone, and you just move the k disks that are on top of it.
So 2 to the k minus 1 plus 1?
It would take you this many moves to move the ones on top over to another peg. Then you take the biggest disk, move it to a free peg. You're not done yet. You still need to take those disks the first ones that you stacked up, and stack them back up on top of the biggest ring. Well, we do that in this many moves again. That make sense? So you have, leave the biggest one here. So you're gonna, these pegs. You're going to take the top ones, restack them over here, for example. Okay. Then you take the biggest one and stack it up here. And then you're going to take these and stack them back up over here. Okay.
So we do the quantity of 2 to the k minus 1
We
times
do
2.
2 to the k minus 1. One more move for the biggest disk. Then 2 to the k minus 1 moves to get back to here. And that should equal 2 to the k plus 1 minus 1. So there's the outline of the proof. Let's work out all the details now. Okay.
Because it's 2 times that? So
Yeah.
2 times 2.
Yeah, 2 times 2 to the k will be 2 to the k plus 1. Yeah, here. All right. So that's the way the proof works. All right. So we assume that k disks can be moved in this many moves. Now suppose we have k plus 1 disks. So we're going to move the top k disks to another peg in 2 to the k minus 1 moves. right? We know we can do that because that's what we assume. So what's left? The biggest peg, the biggest ring is left. Okay. Then in one move, move the biggest ring to the open peg. Okay, you guys picture that? You take the top K rings, move them over. Takes you this many moves, and take that biggest ring, move it over to the open peg. There's one peg that has nothing on it. Okay, then we're going to restack the K smallest pegs back on top of the biggest ring. Okay, then move the K smallest rings back on top of the biggest ring in how many moves? To the K minus 1 move. And so we've solved the puzzle, right? Now all the discs are going to restack onto another peg. So how many moves was that? So the total number of moves equals, well, we did 2 to the K minus 1 moves, and we did another plus 1 to move the big ring, and then we did another 2 to the K minus 1 moves to restack the top ones back onto the biggest ring. Okay, so this minus 1, this plus 1 cancel out. So it looks like you have 2 to the K plus 2 to the K minus 1. But 2 to the K plus 2 to the K is the same as 2 times 2 to the K. So that's the key to getting to bumping up this exponent by one exponent. 2 to the K plus 2 to the K is 2 times 2 to the K. And then now this is like 2 to the power of 1 times 2 to the power of K. So when I combine exponents, I get 2 to the K plus 1 minus 1. So what did we just show? We just showed that K plus 1 disks can be moved in this many moves, 2 to K plus 1 minus 1. So thus, K plus 1 disks can be moved and 2 to the K plus 1 minus 1 moves. So that's the inductive hypothesis, inductive step. We just proved the inductive step. If K disk takes this many moves, then K plus 1 disk takes this many moves. Since we proved it was true for K equals 1, we can now conclude, therefore, by induction, n disks can be moved in 2 to the n minus 1. Let me just for added clarity for all natural numbers n.